Okay, here we go. So today I wanted to talk about just some very basic statistical mechanics. This is what we voted on, so I'm glad some people could show up. This is just a review of some of the things that are in this paper by a walk in the statistical mechanical formulation of neural networks, which is a paper from about 10 years ago. And so I posted it in the channel. I'm not going to read the paper like I've been doing before. I'm just going to, I put together a presentation just to kind of explain what's going on. And again, please interrupt me anytime. That's the whole point of this, for you guys to know what, to kind of get a handle on what we're doing here with statistical mechanics. So let's kind of start. How do here we go. So the statistical mechanics provides a theoretical framework for understanding neural networks. And this is really an alternative framework to what machine learning people use, which is statistical learning theory, sometimes called VC theory, pack bounds theory. Statistical mechanics is an alternative. In fact, when I was a student, this is what everybody used. So I was rather quite surprised to get back into the field after 20 years of software engineering and discover that everyone had forgot it. And so I'm here to just kind of remind people what's going on. Now, these models were inspired by spin systems and are used to describe memory and learning. And there are literally thousands of papers on spin glasses. And spin glasses were invented by my graduate advisor's postdoctoral advisor, Sam Edwards, and there have been several Nobel Prizes on it. So it's a really, really big field of physics. The key models we're going to look at are the Curie-Weiss model, the Sherrington-Kirkpatrick model, the Hopfield model, and the restricted Boltzmann machine. And that's sort of what this paper that reads, it's very dense. The paper is very dense. So I'm just going to kind of explain the basics, and please interrupt any time. Now, you may recall from some of our earlier talks that when you're setting up statistical mechanics, the first thing you do is you want to put together a Hamiltonian. The Hamiltonian describes the energy of the system. Lee Kuhn sometimes talks about energy models for statistical mechanics. He doesn't really do it using, energy models for AI. He doesn't really use the formulation of statistical mechanics, so it's sometimes confusing to me by what he means by an energy. In statistical mechanics, what we mean by energy is you write down a function, in this case like a matrix. So the general form would be H is minus the sum over pairs I and J, Jij times sigma j, minus the sum over I, Hij. So J are interaction terms. These might be typically like the weights of a neural network. The Hij represents some external field, and the sigma ij are binary spin variables, so they're usually plus or minus one. So this is one particular way in which its spin systems are set up. So recall that typically you want to do something like compute the free energy. The free energy tells you the behavior of the system. So to compute the free energy, you have to define a partition function. If you've ever looked at, say, a restricted Boltzmann machine, you'll recognize the partition function. The partition function in this case is the sum over all possible spins, e to the minus beta h, where h is that Hamiltonian, and beta is the inverse temperature. And F, the free energy, is just minus 1 over beta natural log z. And this comes right out of thermodynamics. If you took a course in thermodynamics and engineering, this stuff comes right out of thermodynamics, free energies. But this is the statistical mechanics formulation. And the idea is you want to minimize the free energy. Lower free energy implies stability. So you have this model of the system. You're trying to minimize the free energy. When you minimize the free energy, you presumably get the best solution. Now, recall in some of the earlier work, in the CETO paper we'd shown, you can obtain you can obtain things like the training energy or the training error and the generalization error by taking a partial derivative of the free energy. So recall in our paper we had this annealed free energy, which depends on the system size. If you take minus 1 over n times the partial derivative with beta of natural log z, this is minus 1 over n, 1 over z, dz d beta. This gives you the training energy. So in other words, the training energy of the system in statistical mechanics is not defined by the training data set. It's defined by how much noise you inject into the system. If you train the system and it's very, very sensitive to noise, then it probably has a very high training error. And if it's not so sensitive to noise, it has a low training error. Likewise, you can get the generalization error by computing the partial derivative with respect to n. So if you add or subtract, you add an example to the training set, you get an expression for the generalization error. So this is the basic formulation of statistical mechanics. Now here in these spin systems, when you try to model statistical mechanics using spin glasses or spin models, what you're really doing is modeling the sigma activation, the sigmoid function. By the way, the sigmoid function was introduced into neuroscience by a friend of my advisor, Jack Cowan. So the sigmoid function actually came from computational neuroscience and then was brought into computational experimental neuroscience and then was brought into AI. And the idea is that the spins, if the spin is up, that corresponds to this side of the sigma activation. And if the spin is down, it corresponds to this minus sign. So the spins are really modeling the activations of the system. It's a very primitive model, but the idea is you're sort of modeling this limiting state of the activation of a system. So the spins are plus or minus 1, and they represent these points on the sigmoid. And of course, in physics, these are real things, like they're magnets, or they're spins in an electron spinning. So the electron spins either right-handed or left-handed. Likewise, it sort of spins this way to give up, or the opposite way to go down. So this is actually a physical system, and it turns out this is a really great model for understanding neural networks. And in the paper, they talk a little bit more. They go into these sort of operational amplifiers, and there's a lot of work and I'm not going to go into that. I'm just going to stick to the basic theoretical physics stuff. But this is your basic spin Hamiltonian. And again, it's just describing the energy of the system, where J are some interaction strength, and N is the number of particles, or number of spins. Notice that H, this is an average. So notice that it's an average energy, not a total energy. Now, at least in this particular formulation. Notice that, so why do we want to look at the Curie-Weiss model? So it's very simple, but it's very powerful. It captures the fundamental behavior of phase transitions. And this is really the key idea of statistical mechanics, is that you can see phase behavior. You can't see phase behavior easily with statistical learning theory. This is what all the double descent stuff is about. That you look at double descent, there's this weird phase behavior. Statistical learning theory doesn't describe phase behavior. You have to kind of go back and patch it up. So this is why statistical physics is interesting, is you can get this sort of phase behavior. And the phase behavior is related to learning. Now, in a spin system, what we use in these models is a mean field approximation. And I'll explain what that is a little later. But basically, in the paper, they talk about sort of two approaches to doing statistical mechanics. You can do renormalization group, or you can do mean field. You'll see in the CETO paper, we do both. But the idea is the mean field is sort of the simple way of treating systems, that you don't have to do this very fancy renormalization group. And what you do in physics is typically an order parameter that controls the phase. So you'll recall I said, we compute the generalization error by taking these partial derivatives, but you can also just measure the average spin or the average magnetization. In other words, how many spins are up versus how many spins are down, and that gives you a measure of where the learning is. That tells you something about the phase. And there's a very deep connection between this very simple model and what is this Hopfield model, which, John Hopfield won the Nobel Prize last year for development of the model, and he was the one who really recognized the relationship between neural networks and spin glasses and pointed this out. So what does it mean? So when we talk about spins as a form of learning, there are these two phases. There's a paramagnetic phase and there's a ferromagnetic phase. And again, this is just like a magnet, like your refrigerator magnet. You have if the spins are randomly oriented, the temperature is above some critical temperature, and they're just random. And when the temperature gets below a certain critical temperature, all the spins add up. So this is just like if you took a magnet and you heated it really, really hot, and then you let it cool down slowly, it would lose its magnetic properties. What would happen is if you kept it at that temperature, it would no longer be magnetic because all the spins would be randomly oriented. And the idea is that this ferromagnetic phase of the spins being oriented corresponds to learning in a neural network. When the weights and the activations learn patterns in the data, the spins become organized, and this organization looks like a ferromagnetic phase. And when the system doesn't know what's going on, and it's not learning a lot of information, you're in this paramagnetic phase. And this is exactly analogous to what's going on in Weight Watcher. When we talk about the various phases in Weight Watcher, when the alpha is very, very high, the weight matrix looks random. That doesn't mean it hasn't learned anything. Remember, these are complex systems, but it looks like a paramagnetic phase. And when the alpha starts getting smaller, it starts entering this ferromagnetic phase, and the system is learning. So this is sort of where these ideas come from. It goes back to these very simple models. So learning is a phase transition in statistical.
Hey, sorry.
Go ahead.
I actually have a comment.
Please.
I remember you saying that you were deriving everything from first principles. You were not doing any analogies.
That's correct.
But like what I see here, it's an analogy, isn't it?
Well, this is an analogy. Well, a lot of condensed matter physics is based on analogies. This is an analogy because we're using a very simple model. But it turns out that when you look at other models like Hopfield models or restricted Boltzmann machines, you actually do see these phases, and these phases do correspond to specific states of learning. So I'll show that as we go down. So
okay.
Right. So this is a model. I mean, in some sense, it's a model for a neural network. So you have to. As with all theoretical models, you're modeling a very complex system. But in a physical system, this is real. Like in an actual magnet, this actually happens. And the idea is that you want to. And by the way, we do see phase behavior. So when you look at Weight Watcher, like you look at some of these grokking experiments, for example, that one of our other members on the channel is doing, you will see this phase behavior in the system. And what you see is the phase behavior corresponds from moving to disorder to order. And in the Seidel paper, we do derive this to some extent, that we do derive phase behavior. It's just much more complicated than what you see in these earlier, smaller models. So the idea is that before there's training, you're in this sort of random state. But, we have this, you're random, you're paramagnetic. During training, when you begin to learn, the system approaches criticality. So the system is learning correlations. And then after training, the system becomes ferromagnetic and the patterns are stored and retrieved. This is your basic model of learning. This is the basic neural network theory of learning. That you have these phases of disorder, of criticality, and ferromagnetic of memory. And all systems exhibit this. And again, in Weight Watcher, this corresponds to these random phases. The criticality corresponds to alpha equals 2. There's this critical exponent that arises in this renormalization group transformation. And then the memorization occurs when alpha drops below 2. When the system starts to memorize its data, it doesn't generalize as well. And you can see all this empirically. What do we mean when we say mean field? When we say mean field, what's happening is that you have this very complicated Hamiltonian. You can't really solve it exactly. So you have to make some approximations. You make something called a mean field approximation. It simplifies the many-body interactions by replacing them with an average effect. I talk a little bit about this in the Seidel paper when setting up the annealed Hamiltonian. The annealed Hamiltonian is like a mean field Hamiltonian. So the idea is that, recall earlier you had this very complicated Hamiltonian, which has all these pairwise interactions. This is, you have this, you have n squared or, n minus 1 over 2 interactions. This is very complicated to treat theoretically. So when you get to mean field, you just say, well, I'm just going to assume the Hamiltonian is just a sum over of just pair interaction, of individual interactions. So every spin has its own sort of average interaction associated with it. And the magnetization turns out in the Curie model, satisfies a very simple equation. It satisfies this iterative equation. So the total magnetization, in other words, how many spins are up versus down, it satisfies tan H beta Jm. So it turns out this is a problem you can solve exactly. And so that's why physicists like the Curie model, the Weiss-Curie model, because you can solve it exactly and you can see the phase behavior. And again, M is just like the total magnetization. How many spins are up? How many spins are up?
Yeah. Can you talk briefly about the derivation of the hyperbolic tangent here?
Yeah. I'm gonna explain it now. Like I'm not gonna derive it for you, but I'll explain the idea. So when you do this rigorously in statistical mechanics, there are two things you do. You form a saddle point approximation, and you take the large n limit. And I go through this in the Seidel paper. We do this several times, where I'll explain what the saddle point approximation is. I give some examples of it, but obviously the examples in the paper are more complicated. But the idea is you define an order parameter. So you say I'm going to have m is going to be some order parameter. It's just the sum of the spins. You know, are they? Remember, this is just plus or minus 1. So if all the spins are 1, this is going to be 1 because all the spins are 1. There's n of them. It would be 1 over n, so it would be 1. If all the spins are down, this would be minus 1. And if they're just randomly assigned, this would be 0. Then you define a partition function, which is z, which is the integral over all possible spins. So we'll assume the system now goes to the infinite limit. So instead of taking a sum, you take an integral over all possible spins. You take e to the minus beta in f, where f is some equation you're trying to find. This is this effective free energy. And then you evaluate this by doing a saddle point. So you say, I'm going to say that z is approximately with a minus n beta f m star, where m star is the optimal configuration of the system. And you solve for a df dm, where you solve basically the saddle point being that df dm is 0. And if you go through and solve this, you'll find that you can get that expression for the magnetization. This is how they do it. I won't do the derivation entirely, but we could do that another time if you want. But this is the basic technique. So if you understand saddle point and large n limit, once you get to, you've got like half of statistical mechanics. You begin to understand this is the trick that they use. This is what they're doing. And when you solve this, if you get the average magnetization versus the temperature, you get an equation. So when you solve this f, you can get an expression. It ends up being an iterative equation in m. And you get and so you'll get this average magnetization, and you can plot it versus the temperature. And you can do a simulation, and it turns out the simulation, the theory match almost perfectly. This is something to comment on, that the fact that the simulation matches experiment is very important, because remember, we took the infinite limit. We took n to be very very large. There's a huge number of spins. And obviously, when you do a simulation, you don't have an infinite number of spins, but you get very good results. This is one of the core ideas of statistical mechanics, is that you can apply it to finite systems and you still get good results, even though you're nowhere near the infinite limit. This is one of the reasons why people think the theory works. It's because even though you're in the infinite limit, it still works in these, they maybe have 1,000 spins, or I don't remember what the paper is. You might have 1,000 spins, or maybe only 100 spins, and you still get very good results. The other
right, and quick question: the spins correspond to the neurons on a layer, let's say, in a network.
Yes, the spins correspond to the activations. So
right.
This is you have a neural network with a sigmoid activation, and it corresponds to plus or minus 1, right? The outputs of the, so instead of a ReLU, it's like here I put it's typically a sigmoid, but it could be a ReLU also. That's what they correspond.
Like technically, sigma is from 0 to 1. Not from -1 to
1. It's just a scale issue, right?
You
can make you just change the scale. I mean, physics, it's meant to model it. So the sigmoid just depends on how you define it. So it's not a if you put 0 in, you'll just get weirder results. But everything would still work out the same, because you can always add a constant to this, and it wouldn't have any impact on the experiment. It's just a scaling of the energy. It would just factor out. So the other thing you see is that at this region, you see this interesting behavior near the critical point. So there's a point in this model from, this is the random, you heated up the magnet and it went random. Okay. This is the same, like you could think of the temperatures like adding noise to the system. You're adding noise, or you're screwing around with the learning rate, that kind of thing. There's a point where here is you're sort of memorizing what's going on in here. The system is memorizing. In this region, from t above 1, the system is forgetting everything. And right in this region, there's this interesting power law behavior. Like right in this region, the system is linear. Now you might say, you're just zooming in. Everything looks linear when you zoom in. But this is actually really important. The fact that there's power law decay near the phase transition is critical. This is a characteristic of statistical mechanics systems. And it's exactly what's going on in Weight Watcher. There's this idea that between alpha being, if you think of t as being alpha being above 6, and down here alpha below 2, At alpha equals 2 or between 2 and 4, there's this power law behavior that we see emerge in the correlation structure of the weight matrices. This is exactly what you expect from any statistical mechanics theory, that near a phase transition you see power law behavior. Here it's -1 because this is a very simple model, but all of these systems will exhibit power law behavior near the critical point. And it's not just because you're zooming in. There's something very non-trivial going on here. And this is usually where the renormalization group stuff comes in. But this is very critical. And you see the system transitions from an ordered state to a disordered state. And again, you can work this all out analytically. You can work out the saddle point. I can do it with you. It's fairly straightforward. But this is a classic model of learning in neural networks. So it's very fundamental to any statistical mechanics approach to studying neural networks. Again, so the Curie-Weiss model exhibits phase behavior at t equals 1 for t greater than t. For t greater than critical temperature, the system's paramagnetic. For t less than the critical temperature, the system's ferromagnetic. And, not 1, it's 1/2, excuse me. And there's a critical exponent where beta is minus 1/2. Notice there's a power law which goes t to the -1. Notice it's not the alpha, but it just sort of, it is a coincidence that this is the same as in Weight Watcher, that you get alpha if this were alpha, it would be -2. It would be 2 because it's 1 over. So so you see this sort of power law behavior. That's just coincidence, but it turns out in this system, it's exactly what you see. And I think there was is it 1/2 or 1? I think I may have a mistake here. I think it's 1. I have to check what the critical exponent is. This may be a typo. So sorry about that. I've got to go back and check it. But you can look in the paper. This is from the paper, so I'm pretty sure the critical exponent's maybe I screwed it up. I think it's -1 for Curie-Weiss. This is not a critical point here. Okay, the next model we look at is the Sherrington-Kirkpatrick model. So the Sherrington-Kirkpatrick model is similar to the Curie model, except now you have random interactions. So before, recall, this was just J was a constant. Now we're going to put in these random interactions. So there's an interaction matrix. There's some interaction matrix, and this interaction matrix is going to modulate the strength between this. So this is, it's like a model of the weights in a neural network. You have a weight matrix. So here Ji is drawn from a Gaussian distribution in the Sherrington-Kirkpatrick model, and this is what's called a spin glass. When I do spin glass theory, I don't let this be Gaussian. It's heavy-tailed. But in the classic stuff, it's Gaussian. And if you do this, if you look at the total energy, you get sort of this crazy-looking non-convex function, where there's energy barriers and various local minima and global minima. So when people talk about modeling non-convex systems, this is typically what they mean, is that the configuration space is lots of local minima. It's very rough. And what we know in neural networks is that the loss function for neural networks doesn't actually look like this. It's actually convex. It's ruggedly convex. But in these early models, people use Gaussian spin glass theory, and you get this very flat, sort of very awful type of non-convex loss function. And the goal is to figure out, how do I find the global minima of this thing? So I won't talk much about the SK model. This is sort of their approach. The next model you would get would be the Hopfield model. And so in the Hopfield model, it's similar to this model, except how do you pick the J's? Instead of picking the J's as a Gaussian distribution, you pick them using the Hebbian learning rule. So these are actually the patterns. So the J's become the covariance matrix of the data. So you have patterns, you have P patterns for each vector of the data, some training data set. You pick the patterns this way using the Hebbian learning rule, and you get what are attractor dynamics. And so this works like an associative memory. And this is what Hopfield won the Nobel Prize for, by working this out. Hebbian learning is what we call online learning. So you add one example at a time. And so by adding one example at a time, you can simulate, it's what we call online learning now, or sort of you do one example at a time and you walk down the energy landscape. Now, the Hopfield model, like the Curie-Weiss model, has a phase diagram. And the phases are much more complicated. So recall in Curie-Weiss, there was just one simple phase. Here you have a very complex phase where alpha Here, alpha is the number of patterns, the number of training examples over n, the number of neurons. Number of training examples over number of neurons. This is called the load. And so it turns out that when you train a hot field model, depending on how many patterns you put in, you get different phases. This is characteristic, again, of all these statistical mechanics models. You get this paramagnetic phase. So it's very high temperature. It's way up here. And nothing is ever recalled. There's no memory. You can't remember anything. There's a retrieval phase. So the retrieval phase is here. Retrieval means a hot field model can literally learn from a single example. Like if I have 10 classes and I'm trying to learn how to do digit recognition, you put in one example per class. Sometimes it's called a prototype method. And so you get the retrieval phase when you have very low memory. The hot field model can reconstruct. It can reconstruct its memory. You give it like a partial memory, it will be able to reconstruct what it sees. But the hot field models are models of what are modern LLMs. We actually think LLMs are widely over-parameterized so that in an LLM, N is enormous. The effective number of neurons is enormous. And so you're in this over-parameterized model, and most people, we sort of model the LLM sort of being here. In the spin glass phase, although you could be in the LLM, you might be in a spin glass plus retrieval, meaning that you get patterns which interfere in each other. So this actually might be a cause, for example, where hallucinations come from. And there are some models of hallucinations with hot field models, but the spin glass phase, basically, it's a mixture phase. So some of the spins are aligned and some of them are not. And you get this sort of this sort of behavior where you get the memory works, but it makes mistakes. And then there's the pure spin glass phase, where everything is just, nothing makes any sense. It's just a pure mess. The pure spin glass phase is a mess. You don't want to be in that phase. So in other words, it's generally, the hot field model works best at low temperature with very, very few examples. And if you increase the temperature, if you increase the load above a certain point, you end up in this, you can end up basically screwing it up. It gets confused between the examples. And again, this is worked out this is a theory. The hot field, you can work out this example. There are some extensions of the theory, but this is sort of the mean field picture predicts this. And again, people do experiments. It's a good match. It's not perfect. And you can improve the hot field model. You can improve the theoretical description to get an almost perfect match. But this is one of the examples, again, of this phase behavior that you see in these. Again, it's a very simple model, right? It's just I have spins. I have some matrix of interactions. In this case, the matrix of interactions can be chosen by just looking at the patterns themselves. The weight matrix comes from the covariance matrix of the data, and you get this phase behavior. Right. So here's sort of the example I put in here. I talked through it, but basically this is the different phases of the hot field model. Something to point out. I know the spin glass phase is analogous to overfitting in machine learning. So this is an important concept. The whole idea of overfitting in machine learning means that in statistical mechanics means when you're in the spin glass phase, the system can only retrieve the training data. It gets stuck in these spurious states, and it can never really generalize. So when you talk about systems that don't generalize well, we think about them being in the spin glass phase. But there's also this other phase, which is this coexistent, where some patterns can be retrieved, but others are not. And so there are unstable memories due to pattern interference. Again, people talk about hallucinations in LLMs. It's like, well, go back to 1982, and these models, again, this is a retrieval model, so it's trying to reconstruct its memory, and it makes stuff up. So hallucinations have been part of the hot field model since it was invented. Everyone's understood this. As soon as it was invented, within a couple of years, people worked out this phase diagram, and they understood immediately that this would happen. Finally, they talk in the paper about the restricted Boltzmann machine. The restricted Boltzmann machine is, of course, was given by Hinton, who also won the Nobel Prize. The reason Hinton invented the restricted Boltzmann machine is because he was trying to solve this hallucination problem in neural networks. It turned out in the phase diagram of a hot field model, again, the load, in order for a hot field model to retrieve its memory, the load has to be very, very small. I mean, you can only give it a few examples per class. And if you give it too many examples, it gets confused. So the idea of the restricted Boltzmann machine, or the Boltzmann machine in general, was to add these hidden units, these latent variables, so that you could add more and more patterns, and that the latent variables would learn the patterns. And that way you could add lots and lots of training data, and you could train the system with a lot of training data, and it wouldn't have this problem with the spin class. This is exactly why he invented it. The restricted Boltzmann machine also has an energy function. Here, you're not just picking you're not just picking Jij as the covariance of the data. You're actually learning the weight matrix from the data. And so there are ways of learning the restricted Boltzmann machine. You can actually learn a restricted Boltzmann machine by minimizing the free energy in a two-step process. Hinton doesn't do this. It turns out there's an old paper called Extended Mean Field Theory. You can actually solve a restricted Boltzmann machine using mean field theory, and you can work out the solver. It just turned out it never became popular. The implementation, I have an implementation of this on my blog from like 10 years ago. It just turned out that nobody did it that way. They used contrastive divergence, if you know anything about RBMs. But you can solve it using mean field theory directly. And I have a blog post where I derive all the equations using mean field theory, and I go through this and show exactly how you would do it. And it looks sort of like the primitive version of backprop. So you can solve it. You can solve it using the mean field theory. Just nobody does that way. Computer scientists aren't physicists. They do things their own way. So, but the idea is that you have these visible and hidden units that were introduced, and then you have these biases, and the idea that there's no the key property, there's no interlayer connection. So the RBM is a very, very simple thing. It turns out that if you go and solve the mean field approximation for the RBM, it turns out the partition function simplifies. So typically what you see you don't always see the RBM written this way. You'll see it written in terms of these sigmoid activation functions. So the probability of a hidden unit given the visible unit is the sigmoid times sum over Wi Vij. So again, this is a mean field, right? So you have a sigma, you have a sigmoid. This is your spin. That's why we call sigma is the spin, but it's a sigmoid function. And the interaction that you see in this is a sum over Wij. So you're averaging for every visible unit, you're averaging over all the weights. So again, if we go back to our mean field picture, there's a sigma, you have a sum over I. Sigma I is your mean field Hamiltonian from the Curie-Weiss model. You go to restricted Boltzmann machine, sigma sum over, you have a sum over I, so you're gonna have a sum over I. So you have and this over this average, this is a mean field. And so this simplifies the partition function terribly. You end up with this simplified version. If you go and look at, and what you get is an effect. So you can actually eliminate the hidden units. You eliminate the hidden units from the partition function. Even though they're there, they vanish in the mean field approximation, and you get the simplified partition function. If you go in, and you may not realize that basically the sigmoid unit that you have in an RBM actually comes from taking this energy function and applying a mean field approximation. And so and again, you can actually write a solver doing this as well. You can actually solve the entire problem using mean field theory. We could talk about that another time. That would probably take me about an hour to go through, but I'll send you a blog post on it. And again, so now you get sort of this effective Hamiltonian, which after you sum over all the hidden units, you get an effective energy function, or an effective Hamiltonian, which only acts on the visible units. And so you get a sum over Ji, and again, you get this sum over Jij, where Jij is now the correlation between the weights. So you have a sum over mu, Wij, J mu. You may recognize this from Weight Watcher theory. This is what in Weight Watcher theory, we take the weight matrix and we form this covariance matrix of the weight matrix, and we call this X in the theory. But this very similar object appears in RBMs. This turns out to be the coupling. So in other words, this is the coupling. This becomes the coupling between the hidden units. You average over all the hidden units, and you end up with this effective matrix. And then there's these bias terms. So this links now RBMs to restricted Boltzmann machines and a Hopfield network. The weights define an associative memory, and there are also these sort of sigmoid networks. The hidden units transformed. The hidden units become basically sigmoids. And in a spin glass, you assume these weights are random and Gaussian. They're random and Gaussian, as opposed to, say, Pareto heavy-tailed or correlated heavy-tailed. And the RBMs actually resemble a spin glass system. And you can actually solve for the phase diagram. It's not in this paper, but you actually work out the full phase diagram for an RBM, just like you would for a hot field model. And I think some Japanese researchers, I recall, have worked this out. So to summarize, statistical mechanics provides a framework for neural networks. There are a variety of different models you would see in the literature. The Curie-Weiss model is very simple. You could solve it analytically yourself, and you get all the basic phenomenon. You get the phase behavior. You get critical phenomena. All of this comes out of Curie-Weiss. SK introduces disorder and complexity. Solving the SK model requires much more sophisticated analytic techniques. You can do it analytically to a certain approximation using something called replica theory or cavity method. It's very complicated. We could go through it at some point if you want. Hot field model is the same way. The hot field model, it connects us to associative memories. It really is a model for LLMs as well. To solve it, you get more complex phase behavior in the hot field model. And then the RBM is really a pure statistical physics model, which was designed to fix the hot field model, to fix the hallucinations or the problems in the hot field model. And it is really a statistical physics model. And even though when you might learn about the RBM from a computer science class, they don't tell you this, but it's basically statistical physics. It's a pure, and you can solve the entire problem and get the phase behavior. You can write down a solver. All of it comes from statistical physics. So that's sort of my sort of bird's eye view of this paper I shared on the channel. Kind of a quick introduction to statistical mechanics. Does anyone have any questions I can answer?
Yeah, can you go back? Excuse me. Can you go back and kind of elaborate more on that the criticality with the alpha and temperature?
Sure.
In particular, and how that ties us back into the
HCSR theory. Yeah, sure. So here, again, if you solve the Curie-Weiss model, again, what do? You have this model which is sort of like these magnets, and you want to. So what is the average magnetization? So you're just asking. And I'm sorry, these should be up and down as opposed to left and right. But this is magnetization of 1. All the spins are aligned. Think of them as up. I'm sorry, when I generated this, I should have made them point up instead of sideways. But think of pointing to the right as 1 and pointing to the left or just randomly as something else. These are the activations. And what we're trying to understand is what is the average activation. So when does the system learn? You write down the mean field. You compute the average activations. You write down a partition function. You evaluate it using a saddle point approximation. All this is done in the CETO paper for for Weight Watchers theory, to derive HCSR. You end up with this interesting phase behavior. The average magnetization, if it's below, when the temperature is low, the magnetization is 1. So it goes all the way up to 1. So you get things align, right? So you'll start to align. And so you've learned some memory. You've got some memory that you now know. You have a memory, right? Because you can remember a pattern. When temperature is too high, system looks random. So the analogy in Weight Watcher is that when the alpha is, say, above 6, the weight matrix looks like a random matrix. It may have some signal in it, right? I mean, you can see, look at this. Maybe this spin and this spin is correlated and anti-correlated with this spin. There's this sort of little circuit or something here. Maybe these 3 things are correlated, but it's very, very weak. It could be random. It could be correlated. You're not really sure. And so the weight matrix looks random when alpha's really high. If alpha's below 2, then everything is correlated. You get this alpha of 1.5, 1.6. All the correlations interacting. Everything is correlated. Everything's lined up perfectly. Well, that's not great either. I mean, remember, this is a toy model. If everything is lined up perfectly, it means you aligned perfectly to the training data, and you're going to have a real problem generalizing. If you get some system where all the spins are just a little pointed up a little bit to the, maybe pointed up a little here, it won't recognize it. So that's what we mean by in the ferromagnetic phase. There's these phases of randomness, which is, the randomness is kind of broad, right? The randomness, like this is perfect. Remember, this is perfect. And this sort of is broad spectrum. Then there's a phase transition, and bam, this is memory. This is learning. You see, this is the learning, and then there's this bam. Everything becomes random, and then at this critical point, right between the phase, right where the system changes from memorizing to forgetting, there's this critical behavior. The correlations in the system follow a power law. This is now in Weight Watcher. This phase behavior here, this zoom in region, this is alpha equals 2. This is what Seidel is saying. It's saying that when you're right at alpha equals 2, you're at this phase boundary between learning and memorizing. And when you memorize, you're training, your performance on the test data goes down because you can't generalize as well. So this is sort of this not being able to generalize behavior. Way up here, like alpha equals 2 there's this critical point. In the theory, this is not shown using a magnetization. It's shown because there is a branch cut in the free energy. And there's a branch cut in the free energy, which happens right where the correlations concentrate. So that's a very technical thing, but the idea is the same. And if you think of M instead of being the magnetization, it's the correlations in the system, which is what alpha is measuring. It's the eigenvalues. You get the eigenvalues themselves follow a power law, and it turns out it'll be actually -1/2 in the case of Weight Watcher. But that's what's going on, is that there's this phase behavior, and the phase behavior is described by a renormalization group. And what I think is going on is that the alpha equals 2 is a critical exponent. So it's like this -1 you see here. But we don't know how to prove the critical exponent yet. I just know how to prove there's phase behavior. But this is fundamental to all statistical mechanics models, is that there's whenever you're at a phase boundary, it's thought that in many cases the system is very, very strongly correlated. It's trying to shift between two phases, and there's typically some sort of very, very long range correlations. It's kind of like when water boils and you look at the size of the bubbles. If you look at the size of the bubbles in a pot of boiling water, they're not all the same size. They're distributed all over. There's a fractal distribution of bubbles when you look at water boiling. And this idea that there's a power law exponent here corresponds to the fractal behavior of the correlations in the system. And this is universal in statistical mechanics. It's one of the key things of modern statistical mechanics, is that when you're near a phase boundary, the correlations they get this sort of fractal distribution. You have little bubbles and medium-sized bubbles and big bubbles, and the distribution of those shapes typically follows some critical exponent. And that's the analogy. You would see the same thing, at these phase boundaries between retrieval and spin glass plus retrieval. There are these phase boundaries, and these phase boundaries typically exhibit very, very complex behavior. Does that help, Derek?
Oh, absolutely. It was also triggering some thinking on metastable states, but like grokking, right? We was just, we're in our Discord, we're doing some grokking, and I think grokking is a phase transition. So I guess if you can kind of correlate that and contextualize it based on this paper that you have here.
Right. So these are metastable states. Like if you start getting the spin glass phase, they're metastable. Right? This is very stable. This is totally random. There are these metastable states that exist in the spin glass and spin glass retrieval phases. This is why grokking confused all the machine learning people. They've never seen a phase diagram. So they don't know that learning systems exhibit phase behavior. This is in this statistical mechanics. Even the simplest model has phase behavior. Like the simplest model you can make for a neural network, which is just, a bunch of spins interacting. The simplest model you have for the energetics gives you phase behavior. Just the simplest model. So I think people get confused about things like grokking and double descent because they've never seen phase behavior in any of their models. Um, in statistical mechanics, every model has phase behavior. In fact, that's where all the meat all the meat, is there. Um, so and so trying to flush that out in grokking, what we've seen is you see sort of in the grokking experiments, we see sort of as the grokking kicks in, the test accuracy increases, the alphas all blow up, and then they relax down. So it's like you're in this phase, you're like in one of these phases, and you jumped over here, and then you relax back. There's this weird jump in the system, that it somehow goes from retrieval to, it's basically memorized everything. It's memorized its training data, bam, then it jumps into this phase, and then it sort of relaxes back. I'm not sure if the pre-grokking, I'm not sure which phase pre-grokking corresponds to. Does it recur to retrieval or does it correspond to spin glass? If it were like retrieval, well, we learn everything on the training data, then we approach this phase, and there's like a bam, there's like this explosion, and you sort of, it's almost a hysteresis effect where the system just jumps and then it relaxes back to the phase boundary. I'm just not sure where on the phase diagram it is, but so right now the grokking stuff is still very qualitative. We see this change in behavior, and then we see this relaxation, and it relaxes back to the alpha equals 2. Why does it do that internally? It's not particularly clear, but these systems they can exhibit complex phase behavior. Obviously, when you're training a system, it's not in equilibrium, right? It's not equilibrium until it's trained. It's during the training process, it's a non-equilibrium process, so you certainly could have jumps and things like that. I hope that was helpful.
So the self regularization of the theory, I guess this ties right into why the system is trying to find the most optimum for itself and regularize itself, right?
Yeah, that's when we first saw this behavior. Like, well, it looks like it's just self-regularizes. In machine learning theory, people think SGD is naturally self-regularizing. That's where it came from. People think, well, if you do gradient descent on a complex energy landscape, it doesn't work. You get kind of stuck in these minima. But if you do SGD, you have a little temperature, you can bounce around. So your minimum is here, and you jump up and you go to the global. So people think that SGD has a regularizing effect because it allows you to jump over minima and it allows you to jump out of local minima to find global minima. And so when we wrote the HGSR theory paper, we called it an implicit regularization because our argument was, well, you don't need the SGD. It's a function of approaching this. It's a function of approaching this critical behavior. As the system learns, it approaches this critical. It approaches this critical. Like if you're here, you're random. Temperature is lowering, lowering, lowering. You approach this critical phase. You see this critical phenomenon. The system starts organizing. It self-organizes. And we called it implicit regularization because at the time that was the hot thing in the literature. But this implicit regularization, it's this formation of these low rank structures, right? We talk about the stable rank or the rank, the effective rank, the soft rank of the system decreasing all of a sudden. It's because the system is self-organizing. And that self-organization process seemed to be a type of Tinkenoff regularization where or a type of PCA where all the information concentrates in a low rank subspace. That's where that idea comes from. And that's what sort of we think is happening here. You approach, everything is random, then you approach this phase, and there's this concentration effect. The system is boiling, basically, or freezing, depending on which way you want to
go. So one question, Charles.
Sure.
Have you done any or have you found any relations to the Volterra series?
As I understand it, in the old work by Hopfield, the Volterra equations were used to describe predator-prey relationships, right? Is that what you mean?
Yeah, I mean, yeah. However, I think Volterra series are also used for kind of like nonlinear control. And yeah, I think I found that it's a really good way to probably map what is happening with the idea of uh, attention and the and the multi-layer perceptrons.
Gotcha. Look,
Uh,
in the older days of, I have a paper on this, a short review article on the Nobel Prize that was won, and in this they talk a little bit about the original formulation of the Hopfield model. Hopfield's early model comes from something that was developed by Jack Cowan. If you read Schmidhuber, who's an old group mate of mine. He's totally wrong on this, by the way. Schmidhuber's totally wrong. He thinks that somehow Hopfield stole the model from Amari. That's completely incorrect. The model was developed by Jack Cowan in the late 60s. Cowan's professor at University of Chicago. And these models were based on Volterra, the predator-prey relations. So the original models for neural networks were not these spin glasses. They were originally models of predator-prey relations. They were applications of the Volterra equations. I can give you some references on this, but that's where they come from. And then people realized, oh, we can do statistical mechanics. So then they simplified them, and you got the Hopfield model. But the original models were Volterra. They were models of Volterra predator prey relations. That's where they come from. Schmidhuber will claim that he invented the attention model. That is possible. He may have done it back in '92, or he had sort of a linear form of attention. So that is possible that he did invent some part of it, but he's wrong about the reference to Amari. Both Amari and who was in Japan at the time, and Jack Cowan, who's at Chicago, maybe MIT even earlier when he developed those equations. These are originally predator-prey relationships. That's where they come from. So it would not be surprising that the attention models can be modeled that way as well.
yeah, I mean, they seem very related to Hamiltonians
Yeah.
some way, how. And yeah, I think in the quantum idea, there are kind of this Dyson series approach. And I mean, I don't know, but they really kind of encode the idea of this causality, uh, which I guess really would kind of show how these kind of magnetic things can be via these learning processes, mapping causal data like
Right. I mean,
sequential language or
the early models of statistical mechanics were not this simple. The early models by Jack Cowan on statistical mechanics of neurons, you go back to the theoretical chemistry literature, um, they were looking at the dynamics. So Cowan was studying the spiking neurons, and he was making models for spiking neurons. And the Hopfield model was like a really simplified version of stuff that he did, almost like a spherical cow model of spiking neurons. And these spiking neuron models have very advanced dynamics. They exhibit phase behavior. They exhibit a normalization group. There's all the stuff we talk about. But this stuff that comes from Volterra equations. So it's an application of the Volterra predator-prey relations. So that's exactly what it is. I can send you some of the old papers on it. I mean, this stuff it's older than I am, right? It dates back to like 67, 69, 72, that time when the early statistical mechanics models were made. They're much more sophisticated than this, but that's what they were doing. And then what happened is people realized that the statistical, when you study the dynamics of spiking neurons using these equations, they exhibit stable states. There's a steady state solution of the equations. I don't know if it's a mean field solution, but probably it's a mean field steady state solution. And that steady state solution turns out to be very similar to a Hopfield model. The steady state solution looks like the system is memorizing patterns, and that's where these static models came from. So when you have models like Hopfield or related things like the Little model of memorization, these were models of basically saying these systems exhibit stable point. They're steady state solutions. These steady state solutions are described. There's a matrix of interactions, or the memories are stored in the eigenvalues. That stuff is ancient. I mean, that goes back to like 74 by Little, I think. But even predates Little. It goes back to Jack Cowan's work on this. So, yeah, I can send you some of the old work. But if you look at some of the old literature, you would find it's all based on Volterra predator prey. That's exactly what they were doing.
Yeah, I mean, it's kind of very interesting how all these physical models are kind of allowing us to learn. So yeah, they probably kind of like mirror reality, and that's why they kind of are able to show
Well, that
reality. And
yeah, I mean, the computer scientists may not. I mean, maybe they know they. And now there's so many people doing AI. They're not going to know that in the history of this was, people were studying theoretical chemists were studying models of how neurons communicate. In fact,
yeah,
it was
yep,
really theoretical chemistry that started the field, and then Hopfield discovered this model, and then it took off because so many people know spin glass theory, so it just exploded.
yeah,
But the physicists never made they never made anything useful. There's a great quote by Jack Cowan in this book called Thinking Nets. It was the history of neural networks. He says physicists are like a swarm of locusts. They just study the same problem over and over and over. And what he's talking about is spin glass theory. They just keep doing variations of spin glass theory,
yeah,
which was again invented by my advisor's postdoc. Spin glass theory was invented by Sam Edwards. So, but they just keep solving the same problem over and over with variations on it. But they never produced any code. They don't like you look at like the RBM. I can show you how to solve RBM using mean field theory and using saddle in magnet, but they don't do it. The computer scientists came up with contrastive divergence, and that took off. And physicists they're not computer guys, right? They don't write software, so they're not trying to write packages to give to people. So the field kind
yeah.
of died in that sense.
Uh, one more thing that I've been looking at is this idea of nilpotency. Uh, I mean, in the softmax, by creating this causal triangular matrix, which can be expressed as intensity matrix generators, they kind of have like this nilpotency that is kind of why I guess like you are able to control nonlinearities and kind of have everything collapse somehow.
So by nil
I
potency, you mean that
Yeah,
there's some point if you
just one more thing.
go ahead.
Yeah, yeah, just one more thing. Like I've been getting into the idea of the Navier-Stokes, which is like fluid dynamics.
Right.
Uh, and like this idea of nilpotency, it's out again, which might be why nonlinearities kind of not explode. Uh, and yeah, I mean, nilpotency seems really useful in many cases to understand these ideas. And I guess if they might be also somewhere in these ferromagnetism theories.
Well, by nil potency, you mean if I take a matrix M and raise it to the kth value, it becomes zero.
Yeah,
So that means there have to be some zero.
that's
That means there have to be some very small eigenvalues. So there is a duality between the Weight Watcher work and the structure of the Hessian or the data matrix. I can't remember if it's the Hessian or Jacobian, but there's a duality in the sense that when in some sense the weight matrix in a neural network is the inverse covariance matrix of the data in that particular feature space. So if Weight Watcher has a very long tail, the inverse of that will have if Weight Watcher has if the weight matrix has a tail with large eigenvalues, the inverse matrix will have um, a lot of small eigenvalues, right?
okay.
And so there is and so the inverse matrix would be probably very strongly nilpotent. So the inverse covariance matrix, the covariance matrix of data would be nilpotent. Likewise, if alpha is very very less than much smaller than 2, and you get then the weight matrix itself becomes nilpotent because you basically get a non-trivial null space. So
Okay.
those are two
Thank
things that
you.
might help you. I can see some work guy named Liam who's done some of this work on the inversion. Although I have a blog post on it's very simple. You can see in double descent, like you can see what's going on just by looking at the double descent problem. You can see that the covariance of the data matrix is nilpotent, and that is nilpotent in the sense that it has eigenvalues that are very very small. Right. To me, that means if you have a nilpotent matrix, typically there's some eigenvalue which is close to zero, and so if you raise it to the nth power, it becomes zero, and then the determinant becomes zero. So things get very And typically there could be, you probably have to have some off diagonal elements also, but that I think would be related to what we're doing with Weight Watcher. I can't say for sure. That would be my guess, right? Um, but
So
so
on the
so there's this
outfield
this
phase
notion of.
diagrams,
I'm sorry. Go ahead.
just a quick question. So on the upfield phase diagrams
Yes.
figure, there's a point all the way to the left. There a traversing point between probably 3 or 4 regions.
Right here in the retrieval space.
And yeah, exactly.
Right.
Is there a specific significance to that point? Because it's the
You mean this point here at
traversing.
1, or do you mean the just any?
Yeah.
At 1. Yeah, that's a critical point. That's the critical point between all
Okay.
4 phases.
Well, what is the difference between that one and the overlap line between 2 regions, say? So
Well,
for
because
example,
by a critical point, I mean all the phases come together. So there's a point. Of course, it's not particularly interesting because there's alpha 0. So there's no,
Yeah.
but the in a critical, what we mean by critical point is that in a liquid, there's a point where the liquid, the gas, and the solid are all in the same phase, and
Yes,
it's a triple point. So it's a point where all the phases come together. There's a point where you adjust the volume of a gas and the temperature, and it will actually be a liquid, a gas, and a solid all at the same time.
Yes.
And that's called that's a triple point.
So I guess what I'm trying to understand here is what is the significance of those lines between the 2 regions? Say, for example, R and SG plus R.
Oh, this is a phase boundary between retrieval and that's a phase boundary. So that's a case where you see a distinct. Whenever there's a phase boundary, you see a huge jump in something. So, like if you're looking at when you cross the phase boundary, things can either go first order or you can either see a smooth jump or a giant jump. So you might see a big jump in the spins. If it's depending on whether the phase is first or second order. So these are in a first order phase transition. So like in the grokking, we see a first order phase transition when grokking occurs. If you look in the alphas, if you look at some of the plots in the grokking channel, as soon as the grokking turns on, in other words, you train a model. Grokking means that when you train a model, first it has 0 test accuracy, and then the test accuracy becomes 1 very, very quickly. Or, it becomes high, becomes very, very high, like 80%, 90% very, very quickly. And at that point where the grokking the test accuracy starts to jump, you'll see the alphas make a huge jump. They just explode. They become large. So it's like a first order phase transition. So you can have cases where there's not necessarily a smooth jump between the phases. So remember, this is measuring something like the memory or the ability. In this case, whatever. Like if you go to this picture, you can see a jump like this. Like it doesn't necessarily have to be smooth. So if I cross from, where's the plot? If I cross from t minus t small to t large, you can see, like for example, in this case, if I go from very high temperature and I go along this phase and bam, I jump. That at that boundary, the system could just totally become random. Like it doesn't have to go random slowly. It doesn't have to melt. It could just explode. So that boundary between the phases could be first order or second order, and it just depends on the second order means it goes very slow, like it melts, and first order means it would kind of blow up, like there's a huge change. But that boundary between them.
Wilson's RG is second order, right?
Right. So SG plus R means that all of a sudden the system stops being able to retrieve information perfectly. It just can't do it. It gets confused. And as soon as you cross that barrier, boom, it will get confused. It won't retrieve perfectly. So there's a barrier, a very sharp line between perfect retrieval and non-perfect retrieval.
This is a first order.
I don't remember if it's first order or second order, but you'll see it. Like you'll definitely see the change. Like if you run the model, you'll see that. Like if you run any kind of statistics on the model, you'll see that in this region you'll always get perfect retrieval. As soon as you cross the barrier, you won't get perfect retrieval. And so it could be first order, could be second. I was trying to say the boundary could be first order, could be second order, could be smooth, could be quick. Um, but it's definitely a sharp phase. In other words, it doesn't have to be. It's generally not smooth. It's not like you. How can I say not smooth? So the point is that there's this idea that there was a paper from 2017 in ICLR, best paper ICLR, where they said, we have this neural network and we add noise to it. And we add noise to it, we add noise to it, we add noise to it. And at some point, we add so much noise that the system can't be regularized, right? Like we add a certain amount of noise to it, it works, it works, it works. Then when then you cross a boundary and you add so much noise, like 10% of the data is noisy, 10% of the data has become noisy, and the system totally fails and you can't regularize it. It loses the ability to regularize. And it's not like a smooth transition where if you have 8% of the labels randomized, you can regularize it. If there's 11% randomized, why can't you regularize it with just more regularization? There's not a smooth change in the learning. So that's a phase change. So typically a phase change exhibits some transition. And it could be kind of, it's by second or first order, it's still very distinct. There's a distinct change in the behavior. There's no smooth change. So I may have been confusing. We didn't talk about first and second order transitions, but the point is that there's no like smooth adjustable thing. Like if I were trying to regularize the problem, there's no smooth way of regularizing. Like this side might be regularizable, and as soon as you cross the boundary, it's no longer regularizable. And there's nothing you can do to fix it. It's just in this phase. And that's sort of that would be that's an analogy to what people have got confused in the field about what does phase behavior mean? It means that you can't fix the problem. So here, that maybe like you train a model in this phase, and if you add some regularization, it works really well. As soon as you get to this phase, there's no amount of regularization that will fix it. There's no. It's in a different phase. Does that help?
Okay. Yep.
I hope so. So anyway, if there are any other questions, I'm happy to answer them. Or
I guess that's
go ahead.
Oh, I didn't know if somebody else, but yeah, that's pretty thoughtful. Is that when we're thinking about underfit and overfit, to recover from that, right? Like undertrained easily, you can just train it more. But I guess once it gets to be overtrained or overfit, it's just at that point to where it could collapse. It's no recovery of that.
Well, that's
Right?
part of the problem, right?
Collapse.
I mean, these are that's sort of what was observed in, it's kind of like being like you have to anneal the problem. Like if you get stuck in some weird metastable state, how do you get out of it, right? Like you can probably fix it, it's just that you have to, you got to move. If you get stuck in some weird metastable phase, you got to get out of the phase. So you have to
You got to eat the whole system, or
yeah, you have to backtrack, right? Try to backtrack a little, right? There might be a case where like you try to add dropout, it just doesn't work because you're in the wrong phase. This is what part of the things that's very frustrating about neural networks is that you can't. This is why I invented Weight Watch. Right? You try to look at your layers. If the alpha drops below 2, you should backtrack. You probably won't. You're in a weird state. Being able to get out of that, it's harder to get out of a bad state than to kind of just backtrack and try to avoid it. I can't say that you won't be able to fix it, but you're stuck in you're in some minima. You're learning and you want to be here and you're way over here. You get stuck over here. How do you get out of it? You got to the wrong phase, but you're in the wrong part in phase space and you can't get out. So, and if you try to jump over, you might, if you try to heat it up, you might think you're going to go from left to right, but you might end up over here. You might heat it up and really go downhill. So you could really screw up, right? So if you get in some weird part of phase space, it can be difficult to get out of.
So, like certain techniques like distillation, pruning, and so forth of trying to, pretty much cut out to get the effective correlated space. You can't. In other words, once you can do an alpha hill and get the estimate of the shape, right? You get the shape. and you see if it's heavy tail or not, or what's going on. But if it's not heavy tail, you just trying to cut out for alpha 2
No,
isn't
yeah,
necessary.
yeah. I mean, there may be cases where you want to be a little overfit. There are some cases on the Weight Watcher examples page where it, like being a little overfit, some features being overshit could help you with zero shot learning, right? You might find that if you want to do zero shot learning, you have to memorize some abstract features of the system. But there are other cases where like you see it with the grokking, like you just keep training with the grokking, and all of a sudden it starts getting overfit. It just stops. Like now how are you going to get out of that? Like over more training doesn't help you. Like there's this example in the grokking where the grokking all of a sudden the training the test accuracy gets really high, and then it starts to go down. Well, you can't keep training; it's going to get worse. What did you do? Like you have to stop. You have to go back. Save your checkpoints, right? That's what you should do. Um, so as for the Alpha Hill thing, I'll comment that that's something that Michael students did because they don't want to use Weight Watcher, so they decided to copy. You'll see some of the other papers they talk about the Hill estimator. The students refused to use Weight Watcher, so they rewrote the whole thing themselves, and it doesn't
Yeah,
have all.
it's kind of bizarre, right? Because I was like, is this alpha raw
Yeah,
alpha? Is it alpha
it's
weighted? What was it?
you know
I couldn't.
working with the university is kind of like a pay to play system, right? I invent all this stuff, then I have to kind of give it to the students so they have something to do. I mean, I'm not involved with the university, right? It's just I'm in my
Right.
bedroom, right? So but
Right.
they are just they don't, the university doesn't pay me. I don't talk to the students. I have no idea what they're doing. So I invented all this stuff, and some students come to university, they think they want to work on it. Of course, they have to come up with something new. So let's change the optimizer. Let's make a new version of alpha, and then let's not use this guy's code. We'll just copy it ourselves. I mean, thanks a lot, guys. And of course it doesn't have any of the advanced features. It doesn't do the fixed fingers. It can't detect the dragging. It
No.
can't, right. So it
No.
doesn't do that, and it doesn't. Our stuff's optimized on the GPU. But there's this claim they make in the paper, like, the Clausen estimator isn't stable and the Hill estimator is more stable. I'm like, I don't know where they got that from. That
Right.
there's no, they just said that. Like, there's no evidence of that. There's no.
Right.
I saw them, like, it's so irritating. Now they don't even reference me. I give them ideas. They don't even cite me. But what they're doing, I mean, but
no
this,
love, no,
no,
love.
not at all. But this is what they say. When the Chinese copy your work, that you're successful, right? So this is what they're doing. I mean, it's just a little irritating. But no, the Hill stuff, I have no idea what the Hill. I mean, typically the Hill estimator is thought to be worse because
because it's not the same alpha as it.
No, it's not the same. Of course, and you could see that the alpha equals 2 and the dead X lines up perfectly. So I don't know what but it's hard to say because the Hill estimator is discussed in a book by, I don't even have the book here, by Dieter Sornay. And he talks about, in Dieter's book, I'm going to stop screen sharing. Well, I'll leave it on until we talk. In Dieter Sornay's book, he talked, and Sornay is sort of the guy, is one of the pioneers of some of the, Sornay's he's a counterphonics guy. So I worked with one of his students when I was at BlackRock. And so I learned a lot. I knew about his stuff. And he explains how to use the Hill estimator. And, the whole point of Weight Watcher is something consistent. Like you want to have it, but you use it different. You get a completely different alpha if you use the Hill estimator versus we use the Clausen MLE estimator. Which one is the correct estimator, right? I mean, there is this problem, even with MLE, you have problems where you're trying to estimate things with large variance, and you really want to have a variance corrected estimator. So there are cases with the larger alphas where you need a variance corrected estimator. And then there are cases where you have to so these are things we know about, but if anyone wants to write a paper on various power law estimators, that'd be fine. But it's irritating because, you want to have consistency. The most important thing with science is to be reproducible. If I give you a tool, you should be able to reproduce the result, not just change it all the time and get anything you want. You can use you can get any alpha you want if you. The other thing is that there are, there's a huge battle in the literature on power laws between the physicists and the statisticians. And what happened is that the physicists were going around measuring power law exponents on everything and claiming everything is power law. And then the statisticians came in and said, no, you can't use this Hill estimator. This is nonsense. It's not size consistent. You have to use an MLE estimator. And then they published these papers showing that things they thought were power law were not power law, right? And this back and forth went on for some time. And so so this is a battle I'm trying to avoid, right? You could add the Hill estimator to the Weight Watcher and have it as a flag. It would take, a day to implement. But yeah, it's one of the irritations in the paper, right?
Yeah. Well, I experimented. You presented it, and I wanted to get around to it. I'd seen it before, and I seen it was built on the heavy tail self-organization theory, but then it wasn't. So it was like, because I think the way it was pruning, it wasn't giving me the results. It wasn't giving me the effective result where you got to turn around, you got to retrain it. And then what's the point? If I got to turn around and train it again, right, just to get it to work, then what would be the point of that?
Yeah, no, look, I mean,
right?
these guys wrote this temperature balancing. I suggested to them, look, they didn't understand how things work. And like the way you modulate the regularization of the layer is by changing the layer learning rate. Like that's the strongest effect. If you read the paper, we changed the batch size. And then people don't understand that batch size and learning rate are exactly this. They're inversely proportional. So part of the CETO paper, we have to explain this to people. Oh, you're changing the batch size. People train with large batch size. I'm like, do you understand that large batch sizes mean small learning rates, right? Do you understand that? I mean, so the paper does both just to demonstrate they're exactly the same. But I see you change the learning rate because that's the thing how many things are adjustable at the layer, right? Learning rate, dropout, shape, right? And then I also said if you train with the learning rate too large, the alpha is going to drop below 2 because it overfits.
Yeah.
So, but they so you have these papers that they said, well, try changing the learning rate and see what you do. So I don't know. They invented this temperature balancing thing and started doing all that. The temperature balancing stuff comes from work that Michael did when Michael used to be a theoretical chemist, right, Mahoney, but he didn't. Okay. He quit his. He worked with a guy named Bruce Byrne. Apparently, Byrne was a jackass, so he dropped out of theoretical chemistry and became a statistician. And that's how I know him from back in the theoretical chemistry days. So the idea of a temperature balancing is something in molecular dynamics called a thermostat. But there's no like theory behind it. It's just, we'll just make a temperature balancing, right? It's not like in molecular dynamics, there's an actual theory of this is a thermostat, this is how it works. You're measuring the temperature of the system. You adjust the temperature using Langevin. It's like the whole theory behind why the thermostats work in molecular dynamics. This is just like, let's hack something together. And and we've had some problems, trying, so adjusting the learning rate clearly will speed up the layer training, but there are other things going on. There's the size of the layer itself has to be correct. So things like
I think you dropped a tool, the step law tool, which I think is incredible.
That just came out the other day. I was in shock by that. I saw that on Twitter just today, so I dropped it. And this is
but where the batch size is kind of acting like an L2, and it works dynamically with the learning rate,
right?
Which size portion it. Well, it actually tells you what size, and it's making a prediction of how it will better converge and get to the global minima. So I thought that was a really effective.
That's very interesting, right? Yeah, I thought it was very interesting. Yeah. And because I have this idea, you should be able to change the layer learning rates. You should be able to adjust them. But these are things that we're just beginning to understand, and getting that to work is tough because you don't know what the learning rate should be. Like the theory doesn't tell you what it should be, and you need some sort of reinforcement learning algorithm to go and figure it out. And if you just base it on the alphas, you'll get screwed up because the alphas, pick the Hill estimator or not put the wrong eigenvalues in, pick the wrong minima, and you'll get totally different results. So it's not obvious that you can do that. There has to be something else which would help. So
the weight decay, right? So we was just looking at the weight decay, which was decay to 0, I think, D2Z.
Right, you do weight decay also, right?
Yeah. To look at and then there was another one that was called the Muon. They both are kind of saying the same thing about how actually setting at 0 is effective, is very effective. But I wanted to see because weight decay, or at least the decay rate, and its association with criticality, the alpha
Right. You know,
approximate to
weight decay. There's an old statistical physics paper on weight decay, and it shows that weight decay actually changes the spectrum. It changes the spectrum. So it's a very old idea of weight decay. I gotta dig out that paper. It shows that people use weight. They don't know why weight decay works, right? And there's this idea that it's some kind of a regularizer or something. I remember seeing a talk on this, and people have different ideas of what weight decay is doing. But there are very old papers in statistical physics that show that weight decay is a form of temperature control. That because the weights are it's through the fluctuation dissipation theorem in statistical mechanics that the weights are related to the energy related to the temperature through the fluctuation dissipation theorem, and therefore weight decay is a form of temperature control. And I can dig out the paper. I mean, this is like from 92 or 86 or something like this. When the
so that must have been the original temp balance.
yeah, no, yes, really, yeah. So it's that kind of stuff, and it's like that's why temperature is like this idea that temperature is there's a global temperature of the system is this idea that it's not particularly obvious to me that there's a global temperature, but the idea of why they use the Hill estimator, they don't want to work with me, right? They're I gotta do our own stuff. We're never gonna talk to you, and that's the way Mahoney, he sort of manages things like this, like why, but he's not really involved that much, It's just like I said, it's like a pay to play scheme. You have to have UC Berkeley on the paper, and they're helpful, but I've never really worked with the students. I only really think I ever really did with any of the students was there was one paper where I was on it, where I introduced the random distance metric, and because I invented that. And there are all these other people in the paper. I've never even talked to them. I don't know who they are. I know who these people are. They're on they just put people. Oh, this guy read the paper once. Let's put his name on it. It's just. But
hold on. 1 second. The random distance metrics, right? This kind of connected and correlate that because I was trying to really wrap my mind around that, and I think it was in regards to. Was it the alpha that we were talking about, and then checking the random distance?
Yeah, let me explain. Yeah,
dealing with the eigenvalues.
Let me explain it. It's very straightforward. It's very straightforward. It's just that when they were doing this paper, they were trying to show that the alpha was correlated with the glue score or the blue score from machine translation. So they have access. They train these LLMs. They're able to show that the alpha tracks the blue score, which is some measure of like the quality of a machine translation model. And then at some point it would stop tracking. Go, yeah, because the learning rate's too high. You set the learning rate too high, and the alphas become artificially low because you're overfitting. And you get correlation traps and things like this. And so the alphas can get small when the learning rates are high because you overfit, because you're in the wrong phase. And what happens is that I said, this is ridiculous. You're doing it wrong. So what you should do, if you want to track the blue score or some other measure of the quality of the model, what you do is you take the weight matrix and you randomize it. And then you compare the randomized matrix. You randomize it element wise. And you compare that to the original matrix. And you look at the difference. Well, how would you look at it distributionally? So I just, let's pick, the Genshin-Shannon divergence is like a KL distance, but it's a symmetrized KL distance. That's what it is. And so you just look at distributionally the distribution between the eigenvalues of the randomized and the unrandomized weight matrices. And so what happens is as the system becomes more and more random, less and less, it becomes more correlated, it's less random, and the eigenvalue distributions start to shift. And that's a measure of how random your weight matrix is. And it avoids the problem. Typically what you would do is you'd say, if I want to know how random is my weight, how correlated is my weight matrix, I would measure the distance from the initial weight matrix.
Yeah.
Right? We talked about that last week, but you don't always save the weight matrix. It's people don't save it. And I don't have it. Like if I want to analyze some pre-trained model, I don't have the initial weight matrix. So instead I said, we'll just randomize it element wise and compare the randomized and the unrandomized. And those two should have a certain distance.
Right. And it's going to tell us whether it's really trained or not.
Yeah, and you can see that and you can see that different layers converge at different rates. The problem is that you don't know what the value should be. Like you don't know what is the correct value of the distance. The thing about Weight Watcher theory is that it gives you this phase behavior, right? It tells you alpha equals 2, t equals 1, here's the phase change. And here's the exponent. At alpha equals 2, that's where the phase behavior occurs. That's the optimal point. It tells you what the value should be at the optimal point, so you don't overshoot it. When you're at a random distance, you never know if you're going to overshoot it. In other words, you overfit a little bit. You end up in the wrong space, and you can't tell if you're overfitting. The whole point of Weight Watcher is to provide something like this phase diagram, the Hopfield phase diagram, but to do it for, to do it for a neural network where you would have some kind of phase diagram like this for every layer in the system. That was the idea. Like, I want to have a phase diagram where there's a phase, or like even simpler. There's a phase diagram. You're random. Here you're random. Here you're overfit. Here you're just right. That was the whole point of Weight Watcher, to come up with this phase diagram. So yeah, I don't know where the total temperature. I don't know. Something they came up with. So the hill. Let's just use just use a. I mean, you don't have to use a hill estimator. You could just plot the eigenvalues on a log plot and fit it to a linear regression. That would give you the slope, right? Do whatever you want. I just pick. So the hill. There's right. You go to all this trouble. That's kind of what the physicists were doing, and they would just make
they
a
went
log.
Through a lot of trouble to defy you.
Well,
or at least defy the science.
You have to have. It wouldn't bother me if there was an actual study and you showed that it was real, but you just say it because it sounds good in a paper. I'm like, how does this get through peer review? Why did you take? Why are you doing? You're doing it because you just don't want to use the tool. That's all it is. You want to invent. You want to have your own tool. That's all. But I don't know. I don't know which estimator is best. Is it out? But what we found when we did the Seidel paper is that at alpha equals 2, the estimator worked perfectly, and you can see it in the, Chris Hendricks did these results all, and he reproduced everything independently himself. I asked him, I want you to just try to reproduce these results. Don't use my code. He rewrote the he actually use Weight Watcher, but don't use my training code, and reproduce the results. And we found that when alpha equals 2, the dead X condition is almost perfectly satisfied. So, and we found that was very good. If you use a hill estimator, will you get a better result? I don't know. We could try it. I don't know. Maybe it's better. I don't know. The physicists have their own estimates.
I didn't.
Yeah.
I wasn't successful.
But
I wasn't successful.
Yeah, but it's just one of these things where it's like, it also matters. There are all sorts of little weird tweaks that you have to do to get something consistent, and consistency is, even if you change the way you do the SVD, and if you do SVD with the GPU versus the CPU, you'll get slightly different results because the eigenvalues are slightly different when the GPU, because you're at lower resolution. The GPU, or you use like a fast. There are other ways of estimating alpha. Also, there's another technique which is using. You can use. There's a tool called Weight Watcher Lite, and there's a guy who did his master's thesis on it, and it was they use sketching, so you can compute alpha using sketching. So you don't have to compute. You don't have to do the fit. You can just compute it directly, and you get different results. So that's why the dead X stuff is better, because it's not dependent on a fit, right? It's just these are the eigenvalues. They sum the log of the eigenvalues sum to 1 or they don't, right? It's totally non-parametric, right? There's no fit to it. Anyway, I'll stop. I know we can go on for hours on this. If you get me talking about this stuff, I'll talk I've been doing it for 10 years. So, but anyway, I hope this was helpful to just give people a view of what's going on in like basic statistical mechanics, Curie-Weiss model, and how it describes almost everything. Like qualitatively, it describes the general phenomenon we're trying to get, and how it leads to these different, Hopfield model, Sherringer-Patrick, Hopfield, Boltzmann machine. They're all incremental variations of the same thing. Okay, I'll leave it there. If anyone has I'll leave it there. I gotta head out for a bit. It's and next week maybe someone else would like to present. All right, we can talk about that online. All right. Hey, thanks again, guys. I really appreciate you showing up.
Thanks, Charles.
All right, have a good one.
Take care.